have way too much of this. I'm gonna try my best to give it back to you. You figure it all out. It'll figure it out. Okay, is this you or Reed? That's sorry for giving you back like homeworks at once.
Expect this to turn in 40 hours at once.
It's it's 10 to 5, right? Where is that?
Oh, no, I thought you meant in my whole life.
Oh, okay.
There was nothing else.
Okay, I think that's separated. If some of this is not yours, let me know. It's perfect, right?
No.
I moved it a little closer because I had to watch one of the lectures to find out what was in it, and I was like, you can't read anything on the board.
Yeah. I always see John and Giselle pictures on the board.
Yeah, I'm not doing that. Do you like post that to the YouTube comments or?
No.
The only person who's ever commented is Isabel. It's something about the Maxwell stress tensor. It's actually pretty funny.
Comment on the alien one.
On the what?
On the alien.
You commented on the alien?
I was going to talk about like the dog that touch your butthole.
I never said the word butthole in class. Well, I mean now I did, but
I'm gonna comment on this one. He said,
I mean the funny thing is like it always shows you analytics, right? So it's like average watch time of 26 seconds. So I know y'all are not watching it. It's okay. That's true. Sorry, I have a really bad cough today. I'm hoping it's not contagious. I'm hoping that it's just the fact that the weather is changing. Because I don't want to get sick. Because I'm going to Tokyo in a week and a half. So we have a few things to discuss. Okay. So this Thursday on the schedule is the word exam. Did you know that?
Yeah.
Did everyone do that? Because no one contacted me except for Andres about making a check. So I'm gonna assume that everyone else wants an exam. Is that correct?
No. I'm most likely right.
Okay. So the other thing is that, you know, we're I think this is about as much as I want to do for chapter 9. There's a whole section 9.5 called wave guides. I don't really give a shit. It's like how we talked about fiber optics a little bit and how electromagnetic waves work in media. But we're going to talk about that sort of really briefly here for about 14 pages. And then I think we're done, in my opinion, because I would rather do something that you don't normally see, which is dipole radiation. How do telescopes work? How do like radio telescopes, for example, work? So I think that would be interesting. I don't think that that's a requirement for, you know, you to take this exam. So we can either have it Thursday or we can have it next Thursday. Do you have a preference for doing check-ins this week or next week? So your choice of either an exam and or a check-in, one or the other. Do you want to do them this week? Or do you want them to do them next week and include whatever we're gonna go over today? Thursday. Does that question make sense to everyone?
Yeah.
What? No, next week. So it's this week Today, we'll finish wave, absorption. Thursday. We will either start dipole radiation. Or we'll do an exam. Or on Tuesday, we'll continue dipole radiation, and then we would do an exam next Thursday. And then I will get on a plane and I'll leave.
How long are you gonna be gone for?
Don't get excited about that. No, I would leave Friday and come back Sunday. But like 9 days.
Oh.
Yeah, so then,
So we'll have process.
wow, so that's the second. Okay, so would you prefer not to have class? Okay, so then I should just do the exam then, right?
Thursday?
Maybe,
Oh,
yeah.
yes.
What?
Well, it'll be Tuesday, so Thursday will be Turkey Day. So you get that off already for free. Perfect.
We used to be gone Tuesday.
Yeah, I can't keep track of all this.
There's too many days, we need numbers.
Like, it's not the four things to.
Yeah, it's very simple.
Yeah.
Okay, here's the
Like,
date. Google Calendar. So today is the 7th.
Yes.
We're gonna finish dispersion in media, so. And not like, yeah, you know.
Do we have 3 tests in the final, or is it just 2?
It's 2,000.
Legally, you cannot drop that exam like 2 days before, like, hey, we're having an exam of this.
What's
It's on the calendar.
2 months.
it has?
And
Also, what about the PHYS test?
Yeah, I can do surprise test right now. I can do whatever I want.
Is it gonna be for research? For the Genesis stuff?
Yeah.
Does that say main character in Tokyo? Oh,
That's my first name.
it's Teo.
Yeah, it's my last name. There you go. Main character in Tokyo, yeah.
If you were to host lessons while you're at Tokyo, isn't there like such a huge like?
No, it's someone else doing the lessons that he's gonna be able to do that.
Yes, like.
Like PK.
Or you can watch it with the test. if you take it.
Yeah.
Okay, does that make sense now?
Okay.
Okay. So preference for. Raise your hand if you want an exam or check-in this week. Okay, raise your hand if you want an exam or check-in next. week. 3. You can vote as many times as you want. Just keep your hand more than just, okay, everyone wants it next week? So, 1, 2, 3, 4, 5, 6, 7, 0. Okay, you want an exam on this Tuesday? 1, 2, 3. Over 5, okay, 5. Who wants no class?
But two options.
Oh, I'm not ready.
Haven't checked on
What's that?
Haven't checked on the.
Yeah, if you have the check-in, there's no. Okay, and who wants to guess lecture? 3, 4. Interesting. What's that?
Just randomly voting.
Okay,
You can vote as many times as you want. Okay. Anyone not want turkey? Okay. All right, so it seems like that we will just not do an exam here.
Okay.
So if you don't mind, just send me the email about next week. So we'll do the exam here. And then that precludes this. And so we'll have this.
Look at that.
Wow.
You like it?
Oh, I don't want class.
God forbid you took classes to learn, right? Yeah, this is happening no matter what. Okay.
Those were the books for no class, not for you going to Tokyo.
Just making sure. I just realized that it looked like the boat for me going. I was like, that's not enough. Only boat that matters is my own.
Here,
And yeah, obviously. Okay. All right, so what the hell were we talking about? Why did we get on this detracted portion? Last week.
Oh, we were talking about the free charge and the conductor.
Okay. Okay, we're gonna remember that we're doing E and M.
Yep.
I saw recently E N M on the homework. It's E plus M.
that sounds funny.
No, it's not. It's not like M and M, it's like,
I always thought
But
E and
yeah,
M.
abbreviation
Yeah,
for
yeah.
and, you just take out
can it?
and last letter, and it's just and.
You have to add the apostrophe.
It's like this? Yeah. This is acceptable, but if you drop the apostrophe in it,
And wants to go.
is it before?
Yeah.
Is
Then you should
it
make
before
it,
and after?
you should
It's
go
before
lower
and it's lowercase.
This is okay?
Just put the Anderson in this.
Yeah.
Oh, that's crazy. No, I don't like that anymore. All right. Okay, what were we talking about? We're talking about E and M. We're talking about like free charges or something.
Yeah, we're talking about free charge in a conductor, in a linear conductor.
Okay, what does it mean a linear?
That linear conductor, it has a relationship where what is the J? Oh, the volume current density of the free charge is equal to the conductivity times the electric field.
Let's write that down. Right. Is that reasonable? Okay. So this is applicable for a conductor? And this let us say, what about our Maxwell laws?
Let's say what about what?
What does this let us say about Maxwell's laws?
We can incorporate free charge into our Maxwell's equations.
Good, let's do that. What's the first one?
Charge over epsilon? Or is it
Recharge?
Rho?
Row.
Charge density,
Good. Like that?
but no, not.
No, not. I don't like that. Okay. And then this one? Right. And this one?
The negative dv dt.
All right. Mu
Sigma,
JF
wait.
J.
I'm doing it.
plus epsilon.
That's true. Okay, and this thing here, we just learned was. What? Yes, correct. Go. Right. All right. So this told us something really interesting. If we take something like the continuity equation. Right. What's the continuity equation again? Thinking about it in the context of fluids or in charge.
Change in free charge density over time, negative.
The change in, yeah, the negative free charge density over time. Okay, and how do I explain this to my cousin who doesn't know, you know? How do I use words to explain this?
What was your?
Go ahead.
All this now is charged that leaves the door and comes back in.
Yeah.
Exactly, right? So the rate of change of the charge in a volume is equal to the divergence of the current. So since the current is the flow of charge in and out, the charge times the velocity, right? Where it's going physically determines how much of it changes with time. Cool. Awesome, right? Okay, so this allowed us to write on the left-hand side, we can rewrite this piece like this, dE. And then if I look at this piece, I can take a derivative, right? So I can use this one. And I can use this one. And I can rewrite both sides. Amazing. Yes, why is that an exponential? Yeah. Another acceptable answer to that is because it is, right? Identifying ODE solutions, identifying PDE solutions, you're just gonna know instinctively, yeah, that's just an exponential. Constant and the thing back, that's an exponential. Right? Now you might see multiple versions of this, and when we did the wave equation, that was a different form of an exponential, right? Constant times the thing back. Okay. So this gives us the solution.
Of E to the row L. Oh, row not.
Right, some constant. E, like what everyone thinks.
E to our row. Sigma over epsilon.
Okay, yeah, so we know that it has to be a DDT, so there's gonna be a T in there.
Negative, sigma over epsilon.
Anything else?
Is there? Yeah, there's negative, a negative.
Alright, so how does that behave with time? Decays. No matter what happens, it decays. Okay. And what is this thing?
Oh, it was a time constant.
Right, technically it's 1 over the time constant. But yeah, so a different way of saying this is we can rewrite the exponential here, which is T sigma over epsilon. We could say that that was T divided by T naught, right, where T naught is some constant. Because what we're gonna ask here is that the exponential function at T equals 0 equals 1. Okay, And then at T equals T naught. Is T naught, is two T naught. Three T naught. We know how it goes down. This is one,
Like concave up.
okay, but do we know how much it goes down? Okay. Here's T. T equals 0, T equals T naught, T equals 2 T naught, T equals T 3 T naught. Here's T. Here's the value of the function. It starts at 1. After 1 T naught, where does this point go?
If you run that over here.
Rho naught over E, we're gonna start it at 1, so it'll be
Oh,
good. What's 1 over E?
No.
What's E?
2.7.
2.7, right? 2.7.
Yeah.
Okay, basically 3.
Okay,
A little bit more than 2, a little bit less than 3. What's 1 divided by a little bit more than 2, a little bit less than 3?
around like 30%.
0.3.
Yeah, it's like 30%. Right? Is that fair or no? We'll see how I did that?
Yeah.
Somewhere between 0.33 and 5. Okay. After 2. Correct. Very good. And what is E squared?
5.
I have to be greater than.
Greater than 4 and less than? Very good. That's all I want to know. Okay, so this one will be less than 1 over 9. Or sorry, greater than 1 over 9, but less than 1 over 4. Okay. So it's going down by a factor of 1 over E every time. This is called the E folding. Have you heard of this before? Okay. E folding is when something decreases by a factor of E at every regular interval. So we talk about it in the context of exponentials. You may have seen this before, that we have this like T, this time. This would be essentially what we think of as like a scaled time. There is some scale in the problem itself that lends itself to this formalism. So exponentials are really strange, right? They come up naturally in the world where things decay, right? At a steady rate of 1 over E. E is just a fucking number, right? E is not something special, right? It's not 10. It's a random 2.7, blah, blah, blah. And yet nature loves following this, right? So we talk about it in the context of E folding. This is the amount of time, or sometimes the relative distance, for something to decrease by a factor of 1 over E. Reasonable? Okay. We call this the E folding time in this particular circumstance. If I write T naught, I told you T naught is the E folding time. How do I write it in terms of our sigma and our epsilon? What's that?
Epsilon over sigma.
Correct. Okay. So now let's think about this in the context of, can I understand what the hell I've written? What is an e-folding time in this particular circumstance? Okay, so let's go back to thinking about why we're doing this at all. We have some conductor, okay, got free charge in it. And we were just asking, how does the free charge evolve with time? Okay, and it turns out that the free charge evolves with time in that it dissipates. And it dissipates like an exponential. And it dissipates like an exponential whose time scale is epsilon over sigma. What are these things again? What's this thing?
Permittivity of free space relative.
Free space?
Of the material.
The material itself, good. And this one?
Conductivity of the
The
material.
conductivity of the material. Good. Okay. So let's think about this for a second. If I have a very conductive material, what happens to my T naught?
Decrease.
It goes towards zero.
What's that?
Doesn't it go towards zero?
Yeah, so this becomes very big, this becomes very small, and what happens in the material?
Oh, charge can move faster throughout the material. So it can go towards like the edges.
Ah, you see what we just did? We just defined a conductor. A conductor is something where the charge rearranges itself very quickly to be on the surface. And the free charge inside becomes
Zero.
and yet we have found it. Maxwell's laws show us this. Instead of just defining it and saying, oh, believe this, believe that, we proved it. Very simple. Okay. So here we have the definition of our scale time or our e-folding time. Okay, and we're gonna see this again when we see a different scale height in a little bit. Okay, so let's rewrite this one now. Do I have it here? Okay, I'm not gonna rewrite it. All right. We understand now how the charge density is going to behave with time. And the reason that I started talking about this at all was because I was really curious about whether or not we could ever get a wave in a conductor. Right? Can light pass through a conductor? Yes? How many for yes? Yes? Everyone, yes?
I'm so.
All right, ask your friend for 2 seconds. Spend 3 seconds, ask him whether or not you think light can pass through a conductor.
Think of like.
I think can like impact the surface of the conductor. There's no shot that it goes through it. Yeah. Yeah, it might like slightly change something on the surface of the conductor, but there's no way it goes through. What do you think?
What do you think? Yeah.
No, I think we're talking about.
Yes.
Water is right. So all that means is that like at the surface. Yeah. I was gonna say, at the surface, maybe something happens to water and then distributes and like does get through. That's more like a, I don't know, I guess it depends on what material we're looking at. But I'm thinking of something solid.
Yeah.
So, that's why I'm like, no. Does light pass through us?
There's like lists.
No.
Everything I think about when it
Does
comes
light, oh, I see.
Okay, then.
Like X-rays?
Yeah.
Sure. Fuck, all right, fine.
To be fair, that's talking about visible light,
Oh, you
not
put
like
plastic.
anything like.
Look at them. Are they the same conversation? Yeah.
Well, that's because of the impurities of the water. Water.
Alright. Let's pause for a second here. So what do we think? Just fingers up or down. Do we think that we can get light through a conductor up or down?
Do you mean visible light? Yeah, like what?
I never said that.
Ah, yeah.
I said that.
Figure out,
Yeah.
figure out that.
Everyone likes it, except for you.
Since it's like a
Gotta
blanket
choose.
statement of.
This is like a gladiator, right? The thing, you can't just let him not die. You have to kill him or not kill him.
You know, I think like.
Kill him.
I think light can go through,
Light can go through.
it is not visible.
Okay, so that was a great question, Jose. Okay, because it precludes to what we're gonna talk about, which is the fact that not all light is visible light.
Oh my.
So. Oh, whoa. So in particular, let's say someone decided to call me. I know it's very unusual, right? But let's say it happened, right? How would that happen?
From like a.
Radio waves.
Oh, yeah.
Form of electromagnetic radiation, and in fact, we are in a building. Right, we are, and the building has potentially, hopefully, some metal in that. Right, okay, so let's say I get into an elevator. And someone texts me. Do I get that text right away, or do I get it right after I step off the elevator?
You get it right away.
You get it right away?
Well, it has like.
No, I know. Alright, so here's what we're gonna find out. We're gonna answer the age-old question, the one that is the real reason why you signed up for this class. And that is, why don't I get text messages when I'm on an elevator? Or why does it sometimes take me longer to get them, maybe when I'm underground or in a tunnel? That's what we're gonna find out today.
Yes.
Oh,
it's
yeah.
good.
No. We're gonna do it with math. Just like we just defined what a conductor is based on Maxwell's laws. So now we're gonna do the same thing again, but we're gonna find out whether or not waves can propagate through mediums. And I want you to see how powerful this is, right? We're taking a very abstract concept like E&M, and with just 4, maybe a little bit extra help here, just 4 little extra doodads, we figured out the definition of a conductor, and now we're going to determine whether or not we can use our phone in an elevator.
We can try.
Yeah, we can try right now.
You could try, but we're not going to try. Okay. So let's think back a little bit here. Can I erase this?
Yes.
Yeah.
Okay. We're gonna do some disgusting math, but you're gonna like it. Okay, we're gonna take this E&M part. And how did I get the wave equation last time? Kind of trickery did I do?
It's the.
I did stuff, that's correct, very good. In fact, I did do stuff. So let's write the mu here, and now I'm gonna, instead of having the J, I'm just gonna do sigma E, right? Everyone's okay with this? Get rid of this.
Oh, you manipulated Maxwell's equations. You started with those.
Yeah, I manipulated Maxwell's equations. Inside of a conductor, this is true, right? Okay, but this is also true, right? And this is true. No free currents inside a conductor. We know how they dissipate now. Okay. So what would we do if we wanted to just get, take these fun things together? Get a wave equation. What's a wave equation, by the way?
Like just an
That
example.
is how.
Laplacian
Yeah. That's it.
constant constants equals the time derivative from the source, like the double.
Love it.
Oh,
Space.
second order space equals the second order.
Dope, right? Everyone remembers this good.
Hmm.
Because they loved math methods with whoever they took it with. Okay, how many people are taking math methods next semester? I have 3 of you or something.
I just registered this morning.
Okay. Debating canceling.
I don't know what else to put there.
Alright, fine. If you guys really need it, I'll teach it, but I don't want to. I don't have to. So it's like if I only have to teach 1 class in a semester, I'm so lazy. Okay, yeah. Ceramics. Ceramics. I would be really really bad at that, you'd all be like much better at anything that I do with my hands. You've seen my artistic skills, there's 0.0. I can't even make a throw sound good. Okay, so that's what we want, right? We want to be able to, if we're thinking about getting wave solutions to Maxwell's laws, we want to do two things simultaneously. We want to isolate, say B or E, I don't really care. And we want to put all the spatial derivatives on one side, and we want to put all the time derivatives on the other. Okay? So we did this before, but we didn't have this pesky chart.
Yeah.
Right? But what do we do?
Find a way to decouple it.
Find a way to decouple it. How do we do that?
It's there.
It's there. Yeah, in
Right
fact, it
there.
is there.
Yeah.
Put it over, put it somewhere else.
But it's somewhere.
What's that? Put it on timeout?
Yeah,
No.
Just so you know.
Okay.
can
So,
oh, sorry.
go ahead.
I was gonna say, can we like apply another del?
Another del.
Yeah,
So if I apply a del dot, or what do you want to do?
I was thinking del dot.
Okay, del dot would do what to this side?
I think it's just-
Make it 0. And in fact, that would make this 0 because del dot B is 0.
Okay,
So that didn't help.
didn't help.
But I like where your head's at
Yeah.
because we're gonna use,
The
Del
cross.
cross.
The cross.
so if I apply del cross here, then I have a wonderful vector identity on the left-hand side. And on the right-hand side, I have d dt del cross B, and look, del cross B has all that shit in it, right? So that's just taking the DDT of this stuff on the right-hand side, which I already wanted, which is now gonna relate my double del cross E, which will be spatial derivatives, with time derivative. Precisely what we want, right? Okay. So in practice, what does that look like? It looks like this. Awesome, right? We missing anything?
It's a B.
What?
The E in the second half should be a B. Who did this? Or am I done? Am I stupid? Maybe not.
I want a wave equation.
Okay. Well,
What's missing is this pesky term is gonna show up again. Gonna rear its dumb ugly head.
Oh, yeah.
Okay. So that's the first equation. And here's the second equation. It's really, really different. Questions, comments, concerns?
this would be like,
What do you mean flipping?
not like use replace the E's with B's.
That's not what I did.
That's good.
The last term right there, does that, there's no restricted time.
Oh,
How did I make this?
Oh, did you add another row to, the curl of B?
Yes, so over here, if I do a curl B here, I get the second one. If I do a curl B, sorry, a curl E here, I get this first one.
Okay.
Because this one, curl of the curl of B, gives me something that has del dot B, which I'm gonna get rid of, and the Laplacian of B. So that's the first term.
And then you can get rid of that because both the divergences of B and B are 0 here.
What's that?
You can get rid of like that one term with like simplifying it to the Laplacian. Okay. So let me say it better.
let him cook.
So when you add, when you do like the curl of each one, or when you do like another curl of each one, you get like a divergence of E, and then like the Laplacian. And then you can just get rid of them because both of them are just like the divergence B and B are 0 for the scenario. I think I figured it out.
I cracked your toe.
You can move on.
Okay, so the divergences of E and B are not zero. Right, so sorry, these things here, zero.
Okay.
These ones here, the curls are not zero.
Yeah.
Okay, so here you're gonna apply del cross into here,
Okay.
and the del cross is this.
I get it now.
So why is there no derivative?
So that just takes.
You're right, this is.
Okay, that's a lot better. So, double, del cross something is a Laplacian,
What's that?
because you do the del cross E, and that just is,
Yeah, there's a little vector identity.
Yeah, just.
Right, which I think is something like this.
That's what
Some shit like that.
like that.
Written in the notes.
That's
You've
right.
kept meticulous notes. This is like the third time I've written it. Remember, we had the D'Alembert over there. I showed you how to do it. Back when we didn't have this thing stolen from us.
Yeah.
And so since those were already zero, we can just forget about that.
Bingo.
Okay, cool.
That was my question.
Okay. I don't remember what it is exactly. It might be a half. And it might be minus. But it's something like that. I just don't care. I only care about that. Okay, does that make sense? Okay, but I'm just gonna look at this first one here. So let's compare this. This wave equation? No, it's not wave equation, right? So no. Okay, someone said no. Because that's the wave equation. Yeah. Like the wave back. Okay. All right, so compared to the wave equation, is it the wave equation?
Extra crap.
There's some extra crap. That's really important. So it looks like there's probably some wave equation capability here, but there's potentially some extra crap. So let's recall that maybe with an exception of one or two folks in here, we're not mathematicians, right? Okay, so I don't want to do math. I just like guessing, right? I'm a physicist, physicists guess at the answers and they're right to within an order of magnitude, right? Like factor 5 above and factor 5 below, and we don't really care more than that, right? Okay, so let's ask the first question. We're gonna try a solution here. We're just gonna see if it works. So what's your guess? Yeah, let's just start with E.
The derivative of with respect to time is zero. Problems.
So we have.
This is called, yes, correct. It's also called the trivial solution.
Yeah.
Zero, everything equals zero is the trivial solution. It's technically right, but it won't get you far in grad school. That's solid, okay? So we want a wave solution.
We put like
So we're going to guess a wave solution.
E or something.
Okay? It's gonna work.
Should.
So let's use that. Put it in here, put it in here, and put it in here, and tell me what we get. You write it down for yourself.
Sort of a second order.
No. Take that
Just
exact
do it.
equation, literally do it,
Yeah.
and tell me what we get. We're gonna get something.
Said you didn't do it.
This is plugging, chugging, it's barely bad. Right? I'm not doing any complicated integrals. You'll never see me try to do an integral on the board. I would throw up.
They're right.
I'll get to it.
Well, I mean, would you get? Yeah.
Omega's like a scalar in these.
You can ask your friend, ask your
Oh,
friend.
okay, okay. Yeah.
Yeah.
Got it.
I don't know if they're coming back.
You get something like that.
No, I think you're right.
So,
Space
K is.
Well, I mean, I guess they're not right, but that you just saw this all this.
Yeah.
Yeah.
Yeah. We did it. Did you get this? Reed and I got this. It had to be. I guess there's more we can do with it.
Okay.
I would like to know the relationship between omega and K. That's essentially what I'm gonna get you to. You may have heard me talk about this in fluids. We'll do waves. And then we'll try to figure out what the relationship is between omega and K. And what we do is we assume that it's a wave. And what we find out is that if we assume a wave solution because of the shape of the derivatives, then we find out that sometimes they are related to each other in interesting ways. And that's called the dispersive relationship. How does omega affect K and vice versa? Okay, so in this particular circumstance, I set up a wave. And with this equation, I called it equation 1, because I didn't want to write it a bunch of times. What does that prescribe? What does that force the relationships between omega and K to be? If I assume this solution. You should have K on one side, omega on the other. Everyone have that? Yeah, you have it.
That's something different, but she had it.
What is it?
K on one side.
Yeah, K on one side, look at the equation, right? This is gonna give us what?
Ooh.
Negative K squared.
I only looked at the right hand side. Not the left hand side. So I gotta do the left hand side.
Okay, and this one?
That was just omega. Yeah. Gotta do the left hand side.
So let's see if we can write these all down, okay? So actually, for this one, I get I, K. I get IK. And the IK. That's the left hand side.
Well, you're this, assuming T equals 0.
Don't have to.
This is the coefficient you get when you can see
So since we're taking
You're
it.
taking this,
for the left side.
So notice this is the left hand side.
okay.
Equation 1. Left hand side.
Yeah, somebody not care about the epsilon naught and the E naught, right?
You tell me.
Now this is on both sides.
This is a
This is-
constant. It has to be a constant, right? Because all of my spatial derivatives, my temporal derivatives, I included in the exponential. Right, this is some constant of integration. Not really a constant of integration, it's gonna have a physical meaning.
So you're saying we can just like divide it from both sides? Not.
Well, that's the whole point of choosing an exponential solution, right?
Okay.
Your exponential solution, the choice is that you take something You take a derivative and you get the same thing back times a constant.
That makes sense.
So these are the constants that I get back. Two spatial derivatives, two constant sets. I know. Right?
That's-
Yes or no? Okay, so now let's take the first term. So I'm gonna get mu not epsilon not.
Yeah.
What else do I get? Two time derivatives now.
It's negative now. Yeah.
Negative, I don't think I'm negative, I don't think I'm-
Well, we just.
No, we're not gonna do two steps at once, because we don't trust ourselves with eyes and negatives and blah, 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 okay?
Okay.
All right, next, gonna have a plus.
We're not supposed to keep the E I K Z C.
No, why do we not need to do that?
Well, it would be there, it's all the same
Yeah, so since,
on every term.
yeah,
So it just cancels both sides.
yeah.
Right.
Both sides, yeah. Here, here, and here. So I can take this entire thing, right? The reason I'm choosing a solution that's an exponential is because I want it to wash out. Right, it's gonna be the same here, the same here, the same here. And doing derivatives, it just give me constants back. So depending on how many derivatives, like let's say this is the 9th derivative of x. Right, then I would take 9 constants, I k to the power 9.
What would that even mean? Like,
Oh my god. It's just bad, right?
Yeah.
Okay, alright. Okay, so now what do we get? Plus,
Minus omega.
minus omega,
With the I also.
with the I, good.
and then the constants, omega, or not omega, sigma. There you go.
Okay. What? So what's the left side say?
Oh, it's weird.
Negative K squared.
Negative k squared, is that correct?
Yes.
Because I times I is
Negative one.
correct. And this first one is. These two become a plus. And these two become a negative, so it's negative
Omega. Yeah.
omega epsilon. Like that. Yes or no?
Yeah.
Okay, and then what?
It's
Same thing.
11 letters.
That's not the same thing at all, is it?
What do you mean it's not the same?
It's not the same thing, right? This is different.
Oh, yeah, sorry.
No, it's
I was like, it's just moving. Yeah.
above.
It's a,
Okay, so what's k?
it's the square root of that.
Yeah, but what is k? What did we mean by k?
The wave number.
What's that? The wave, good. So that used to tell us something about the distance between peaks and troughs. Does it still do that?
In this example?
Like it would.
Feel like it would. Raise your hand for yes.
Why would we change it?
Raise your hand for why would it change with me?
Now we've just like quantified what K is.
Yeah, so I wrote k over here. And here's the old version. What does this do?
I guess it's like the conductivity.
Something much more important there.
Oh, the imaginary number,
The imaginary number. K is no longer simply real.
it's complex.
It's complex. So if it's complex, then each section of it is going to affect our exponential differently, isn't it? Okay, so let's see how that works in practice. Okay. So we're gonna rephrase this. Actually, we're gonna call this hey twiddle. To designate that it's complex.
Okay.
And not like, oh, it has a lot going on in its life. Okay. So this is the real part. And this is the imaginary part. Alright. So if I write it like this, I'm just gonna rewrite this a little differently. Okay, hey twiddle is kappa. Sorry. K plus I kappa. Okay, I know, it looks horrible. Relax, okay, alright. So let's imagine there's a real part and an imaginary part, then I could rewrite E as E naught. Okay, everyone's favorite piece. E to the I K Z minus omega T. Okay, and you say to yourself, well, you didn't do anything different with mine. I'm gonna add a second exponential. No, not again. More exponentials. Okay, so this piece here, if I multiplied it into here, it would do what? Okay,
It would make it real.
yes, it would make it real. And the two i's would become
Negative.
negative. That's correct. So now I can write kappa. Let's see. We want to walk that step back, or do we get it?
You walk it back.
Okay, let's start it here.
No.
Hold on, I was. Crackers. All right, so let's do E equals E naught I, okay, K Z minus omega T. Okay, and now I'm gonna stick this thing in here. So that's gonna be E naught E to the I K plus I kappa Z minus omega T. So that's gonna be equal to E naught E to the I A Z minus omega T E minus kappa. We did it. What does that even mean? What have I done? Unbelievable, right? Stupid class. Okay,
So like now there's like imaginary parts.
so now there's an imaginary part to the wave? Is that the question?
Yeah.
Well, the wave started off with imaginary parts, right?
There's a real part.
There's a real part. That's the major difference. So this now looks like a wave. And this is not a wave.
That's like a,
And it's leaking.
it's like a decay.
Yes, it's leaking or it's decaying, right? Okay, so this is an exponential decay times a wave. So you start off with a wave and it's going to decay. Okay, now before we saw an exponential decay of the free charge and we called it an E folding time. This now will be the E folding length. Okay, kappa or 1 over kappa. Okay, so let's write that. You have Z, or let's call it Z naught maybe. Is equal to 1 over kappa. And this is called the E folding length. You may also be hearing the word skin depth. Yeah, that's. You guys, I didn't make this up, okay? It's not like my choice of words. This is what it's called.
Is that in reference to how deep it gets into the conductor?
Oh. Okay, so what this is saying is how far can the wave propagate into the material? And think about it this way. You start off with some wave outside of the medium. Okay, here is the medium on the left-hand side, just like we've seen many, many times. But instead of it being N2, which light is allowed to pass through, now it's a conductor. So the wave hits it from the right-hand side, and by the time that it makes it Z naught, the amplitude has decreased by a factor of 1 over E. Okay, let me say that again, or does everyone get it? Can see it? Okay, so let's just write it up here. On this side, you have the wave, and it's propagating in the Z direction. That always is, right? You have our hand like this, Z, E, B. propagation. Okay, now this wave is the normal part, standard maybe. And this is our Z that's still in the propagation direction. So now it goes into this new material. Here's the conductor. And over here, N equals 1. That would be a vacuum. So as soon as I enter the conductor, now the wave amplitude is moderated by 1 over E. So that would be 1 over E here at a distance of Z naught, very good. And this is 1 over E squared at a distance of 2 Z naught. Very good. That makes sense now?
So the stronger, like, some sort of wave that goes into it, the more it can go inside of the medium.
The answer was yes, for the first question, yes, also.
Okay, so let's answer both of those questions in the order that they were asked. First, your question was, if the amplitude is larger, can it propagate farther?
That's what
Is that true?
No, because the amplitude didn't affect.
So what determines the strength with which depth?
Aha, we'll get to that in a second. But to answer your first question, the original amplitude has no bearing on its penetration. Okay, so 1,000 X-rays and 1 X-ray both penetrate the same amount.
Okay,
Right?
so it's like the property behind the thing itself.
Right, with these properties here, right? It's the dispersion relationship, which is up here, which includes some garbage, right? Okay.
Delicious.
Okay, so in fact, I can write this, I'm so glad you asked it, it's almost like I paid you in this class. So here's K.
Where's my money?
Like I always have the best question that I don't get anything for it. All right, use omega squared plus I mu sigma omega. Okay. Now, you're just gonna have to believe me, but you can do this. That's obvious, right?
Couldn't you just put that inside of the original square root?
I know, but you're gonna see why I wanna do this. So this is not obvious at all, right? So this is like some mathematical mumbo jumbo in order to get it into a format that you're really gonna like, okay?
Like harmonics.
What's that?
Like harmonics.
We're just gonna look at 2 special cases. Okay. And we're gonna use a binomial expansion in one case, and in the other one, we're gonna use just the fact that sigma is much larger or much smaller than omega epsilon. So this is what I want to look at. I want to look at the relationship between the two here. Okay. This piece here is still going to give us the wavelength. But this thing is now going to be okay. So let's look at the first special case when sigma is much smaller than omega epsilon. What does that look like?
I mean,
It'll be small.
for like the second term then, it's much smaller than omega, can it just like, the second term just be more in the square root?
Yeah, let's write this down a little bit. So if I wanna separate out the I and the K, I can do some more mathematical mumbo jumbo. So I'm gonna write it like this. Maybe I'll write this before. Write this like that. Here's the two versions that I'm gonna use. Here's K.
Way better.
Super much easier to understand, right? Alright, here's kappa. It's almost the same thing, but we're gonna change that to a minus. Are you happy you never had to derive this?
Yeah. With somebody else's.
Just someone gave it to you? Oh, yeah, that works. Okay, remember this is the skin depth, and this is the wavelength. Okay, so let's go back and let's make this assumption now. Sigma.
You keep saying K for wavelength, and you mean wave number, wavelength.
It gives you wavelength, right?
This,
In the same way that this gives you skin depth.
okay, now I get it.
Yeah, it's just one.
You got this equation from that one, about it?
Yeah.
Another book, how we derive that?
Well, K is written like this.
Yeah.
So you just have to separate them.
Yes.
Like this. We can do it later if you want. We can do it in the office size.
Would
Yeah.
the cap assertion just go away when it stops? Look at less.
We would use the binomial expansion here. Okay, so. Sigma. Over omega E would be less than 1. Right? So therefore, we would say something like 1 plus a small number. To the power.
Yeah.
N. What is that approximately equal to?
1 for the first term.
Always.
So, yeah. It's like, something. I know, the denominator is like 2 factorial.
Yeah, let's do it like this. No one has a number, it's okay.
No one has a difference.
Okay. Not even that.
You guys don't know this.
They're not just really excited about that too, right?
Yeah.
Right?
We need the third term.
Remember that notation, O?
Oh, no.
Some computational as well. Of order, H squared of order, H to the 4th.
Oh,
Right, so whenever we do an expansion, we collect terms that are of the same order. In this particular circumstance, these are all terms of order small squared. So we're gonna let those be away. And this will be the binomial expansion. Okay. So in this particular circumstance, we can write that, right? I have to collect all of those dumb terms together. Did I say? This is kappa. And this is the skin depth. Okay, write that one. Okay. And kappa we wrote over here is like 1 over this value. So I could write the skin depth Z naught as the inverse of this.
Yeah, I was gonna say, wait a minute. Okay.
What have I said?
We now have a way of relating conductivity to the depth.
So in this particular circumstance, we said that conductivity is big or small?
Very simple.
Small. So low conductivity means what kind of material?
Like a insulator.
Yeah, it's closer to an insulator than a real conductor. So I'm thinking in my head, wood. Okay, wood, poor conductor. Okay, so what happens?
So mean to wood.
What?
Don't be so mean to wood.
2 over a small number is what?
1 to 2.
What's that? Big number. Yeah, so now Z becomes long. And if I look over here, that means that Z penetrates farther into the wood.
Okay.
Okay. So I can propagate this E and M wave through the wood.
What does that mean?
Okay, all right, interesting. I wonder if we have the time for the conductor one.
Does that mean like if you leave wood sitting out in the sun, it just gets hot? Like, is that how?
right?
Yeah, like, is that what it does?
You tell me, does wood get hot when it's left in the sun?
I feel like it should.
Yeah, in fact, it does, doesn't it? Everything gets hot when it's left in. Okay, but thermal conductivity and the conduction or the ability to absorb those waves is different. And we'll see that when we think about radiation.
So the center of the wood gets hotter.
Well, so you're now conflating 2 different things.
Yeah.
Okay, you're taking wave propagation and you're thinking thermal propagation.
Yeah.
And we haven't drawn that conclusion yet because we don't know what happens to the atoms inside.
Okay.
All that we've said instead is because there are no free electrons, which would normally take that E and M wave and redistribute it towards the edges. It's doing something to those electrons, but we don't know what yet. Okay,
Kind.
you actually don't know.
Oh, no.
Because we don't know how it affects matter,
Okay.
right? Because sometimes, you're right, it's gonna heat stuff up. But sometimes it's going to re-radiate. Right? We haven't talked about that yet. Okay. You can do the opposite of this. You can imagine the conductivity is very large. And what's the answer we're gonna get, even without doing any math?
Could be.
Z naught goes towards 0. Or like really, really small. Or wait, oh, Z naught would be great.
Well,
I don't think.
Okay, maybe we need to.
hang on.
All right, we'll do the math. We'll do the math at the beginning of class next time.
Okay.
Or you can try it at home if you want.
Okay.
So what we're talking about here is the propagation of waves into a medium. And I'm sorry that we didn't get to the most important question of the day. which is whether or not you can use your phone in an elevator. But I'll tell you now that we will have this capability. I've already written it on the board.
Satisfied.
It's still on.
Yes, yeah, it's right here. Can I use it in the elevator?
Yes.
Well, you don't know it yet, but this will tell you the answer. Okay? Okay.
Yeah.
Can you?
No. When they're next to you.
No.
Does it have an answer?